Hey everyone, today we will be looking at the Gumbel Softmax method to enable differentiable categorical sampling. So a prerequisite to this is I hope you already know what variational autoencoders and vector quantized variational autoencoders are. If you don't, I already have videos on that and they're in my Git repo, so I will link them down below and I'll put some cards above so you can go and watch those first. But assuming you know all of that, I want to do a light recap of VQVAE just to explain why Gumbel Softmax is so important, because we're going to be using it in some more complex architectures like Wave2Vec in the future. So if you remember, in VQVAE, we had a setup like this. We have a encoder and a decoder, just like any other autoencoder out there. But instead of learning some continuous latent space like we did in the standard autoencoder or the Gaussian latent space like we did in our variational autoencoder, we want to learn a discrete latent space. We want to map our data to a set of discrete tokens. And in this case, we have k possible codes that could be. The problem is, how do we map continuous stuff to a discrete thing? And the way the VQVAE architecture proposed was, why not just do the Argmin? We're going to take our continuous output from our encoder, find the code out of our k codes that's the closest to it using the Argmin operation, and use that. The problem with the setup, though, is of course Argmin is not a differentiable operation, which means we now need to do some derivative tricks to pull this off. The main trick was to copy gradients around the non-differentiable operation. As you see here, we're taking our data, we're taking our gradients, and we're just copying it around this Argmin operation we're doing here. But if we do this copying operation, how do we actually train our embeddings? Of course, this is an n-dot embedding. It's just a code book, and this needs to be trained along with everything else. But if we're just copying gradients around this entire operation, this will never get any gradient information to update. So what do? Well, the main setup is we need to add extra loss functions. And this is why the VQVAE also had its codebook loss and its commitment loss and all the other tricks that it used to pull it off. Of course, if you want more details on that, just go ahead and watch that video, but I'm not going to go much more just to keep us on point here. So the VQVAE essentially had this problem that it was a non-differentiable operation. We had this Argmin. So what if we reformulate this problem as sampling? And what I'm going to do is skip ahead a little bit just so we can see this figure, and then we'll kind of go through lots and lots of stuff to get here. Instead, what if we do this? We have some embedding dimension, right? Or we have some embedding here, some vector. And the way the VQVAE mapped it to one of the codes was, why not just find the Argmin? So we'd look at this vector, we'd look at all of the different codes in our code book. So we have 4 codes in this case, and we just select the one that was closest. It's just that operation of finding the closest one was not a differentiable operation. So what Gumbel Softmax does is something like this. We're going to go ahead and take this embedding. We're going to map it to there's 4 codes. So we're going to have a linear layer that's going to take our embedding dim and predict 4 different outputs. This is the same as like when we do image classification. If we have a ResNet, we get some embedding vector at the end that's been pooled and learned from all of those convolutions. And then we map that embedding vector to the number of classes. In ImageNet, there's 1,000 possible classes. So we have 1,000 output vector. Just like that. And so exactly in the same way, we're going to be doing that. We're going to be doing this fancy thing called Gumbel Softmax, which we'll get into in a bit, but that gives us a one-hot-encoded vector of 0s for the codes that we don't want and 1 for the code that we do want. And this is how we identify which code we want. And the cool thing is this whole Gumbel Softmax enables gradients to flow, right? So we still have gradient information and we are good to go. So we're going to build our way up to this. There's obviously a lot here that we need to do. Before we get into all of this, though, we should probably discuss the Gumbel distribution. Just because I keep saying Gumbel, it's probably a good idea to understand where it comes from. So let's go ahead and just do a little bit of an exploration of the Gumbel distribution. And then we'll come back to everything else. So the Gumbel distribution is expressed as this. So it's going to be the CDF, right? So the density function, cumulative density function, is going to be G. That's a Gumbel, and it has 2 parameters, a mu and beta, right? Just like how our normal distribution has a mu and sigma, Gumbel distributions have mu and beta. The mu is the mode of our data, right? So the mode is the most occurring thing in our data. So mu is the mode, not the mean, it's the mode. So a little bit different. And beta is just our scale parameter. And we'll kind of see how that works out in a bit. And the distribution looks like this. The formula is going to be e to the power negative e to the power negative x minus mu over beta. This is the Gumbel distribution CDF. And then similarly, if we take the derivative of this, of course, this will end us with the PDF, right? Little f is going to be equal to, let's see, this is going to be, and actually let's not do the PDF of this distribution. Let's keep it simple. The distribution we really care about is standard Gumbel. So all we really care about is Gumbel 0, 1, where the mode is 0, the beta, beta parameter is 1. And so that's going to be e to the power negative e to the power negative x, because it's going to be x minus 0 over 1, so it's just x. And so our little fx, right, so our PDF, this is our CDF. We then have our probability density function, PDF. It's going to be just the derivative, right, of the CDF. So that's e to the power. This is just going to be e to the power negative e to the negative x times negative e to the negative x times negative 1. So that's going to, by simple chain rule. So we'll end up with e to the negative x, e to the negative e to the negative x, right? And that is our PDF. And so what exactly is this Gumbel distribution? What do we use it for? It's used to model the extreme. So another term for the Gumbel distribution is also type 1 generalized extreme value distribution, which sounds super fancy, but it's a model that's used to model maximums or minimums, depending on how you set it up. But in our case, we'll be looking at it for maximums. And if Gumbel Softmax is used to model maximums, then it just makes sense that we can use it to model our max, argmax operations, that sort of stuff. So let's look at a quick example of how this Gumbel distribution is used, and that should give you a general idea of why it's applicable to what we are using it for. So what I've done here, and I'm not going to write this code, I just went ahead and used it. What I've done is I've set the average temperature for every single year to be 75 degrees Fahrenheit. So that's my average temperature that I think, over the entire year, that's what it's going to be. And I set the standard deviation to 5. And what I've done is there's 365 days in a year, and I have 10,000 years of data. So I've randomly sampled 10,000 years, each year having 365 days, some value with a normal distribution with a mean of 75 and a variance of 5. So we get our distribution for every single year. And my question is, what is the maximum temperature of every year? So my daily temps is just a matrix of the number of years by number of days in a year. So I go ahead and take the max along the number of days. So I get the overall, the highest temperature of every single year. And then I fit a Gumbel distribution to it. Very nice that scipy.stats has a Gumbel built right into it. And we get something like this. We can see that our Gumbel distribution, and in general, our distribution, models that it's very rare to have a temperature of 84 as the maximum for a year, but it can happen. It's very common to have temperatures of like 88 to 90, maybe 92 in a year, right? In a whole year, that would be the highest temperature, and then it becomes less common again for some of this tail end. And so this is my Gumbel distribution, me trying to model the maximums. And this is typically to model the maximum of some distribution, because of course the normal distribution is not like that, but the max of a normal distribution will end up looking kind of like this. And this is exactly why we use the Gumbel distribution. It is to model the maximums. That's the entire intent of it. And so if we can again use Gumbel distribution to model the max of something, then it kind of makes sense that we can probably use it to model the argmax of something as well. And this is what we're going to be taking advantage of. So now let's go back to this figure, which I kind of glossed over, to understand why we use the Gumbel distribution. And to understand Gumbel Softmax, we need to first do Gumbel-Max. So Gumbel-Max came before it, and Gumbel Softmax is essentially a small extension of the Gumbel-Max trick. So let's think about sampling and how we normally do it. In language models, for example, but this can be for anything, but let's just say large language models, we typically want to predict the next token, right? We want to select the token with the highest probability. So how do we do that? We will have, our model will predict the probability of token 1, the probability of token 2, the probability of token 3, ... probability of token, let's say n. Let's say there's n possible tokens that you could have. So we get all of this, but our model doesn't actually produce probabilities, right? What it does is produce logits. So what we'll actually have is something like this. So let's just call them T1, T2, T3, dot, 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 Tn. So these are the raw outputs, the raw logits of my model. After this is going to go through a softmax operation, right? Which is e to the power xi divided by sum j e to the power xj. We're going to apply that, and the softmax is what will actually produce the probability that I want the first token, probability I want the second token, dot, 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 probability I want the nth token, right? That's the setup. And then from here, I have a distribution of what tokens I want, and I can sample it using a multinomial, right? Multinomial distribution. So of course, if you want to do greedy decoding, then you take the argmax. But if you don't want to do greedy decoding, then you want to just randomly sample from my list of tokens with their probabilities. So if I have the probabilities of like 0.2, 0.3, dot, 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 0.1, this means if I randomly sample 20% of the time, I'll randomly sample this token. 30% of the time, I'll randomly sample this token. 10% of the time, I'll randomly sample this token. And that's how we typically sample for LLM decoding. Right? That's just one standard way, and Hugging Face has a great example of comparing standard LLM decoding with what we're about to do, Gumbel-Max sampling. Gumbel-Max sampling, here's the promise of Gumbel-Max sampling, and we will do the derivation proving this to be true. But for now, here's the promise. Essentially, you have your raw logits, just like before, but what we're going to do is sample some Gumbel noise. And this is going to be standard Gumbel noise from a Gumbel 0-1 distribution. Just randomly sample some values, just like we sample from a Gaussian distribution. Go ahead and do that. And we're going to add to our logits this Gumbel noise. Just add them together, and that produces x1 through x4. So x1 is 1 plus g1, x2 is 3 plus g2, x3 is 4 plus g3, dot, dot, dot. And then we're going to take the argmax over this whole list here, right? All these things here. And the promise is that if we repeatedly do this over and over again, just keep adding differently sampled Gumbel noise to this distribution, at the end, the probability of the argmax being x1 will be 3%. The probability of the argmax being x2 will be 24%, dot, dot, dot. And this is the exact same distribution as if I had done my softmax on my logits. So my softmax on the logits produce the probability of the first token is 3%, probability of the second token is 24%, dot, dot, dot. And we get exactly the same results, but by doing it this way. Now this is preferable. This is preferable because look at how much less computation there is. Softmax is actually pretty expensive of an operation. You have to do e to the power every single logit, sum them all together, and then divide every single e to the power of the logit divided by those sums to get this value. Here, we're making the claim that doing it this way gives you exactly the same probability distribution. And that's essentially the proof that I want to do first, the proof of the Gumbel-Max trick. All right, let's go ahead and set up the proof for the Gumbel-Max trick. So the Gumbel-Max trick, like I said, is going to be if y, some y, is equal to argmax I, and we're going to add to our raw outputs, our raw logits, which we'll call OI for outputs, plus some Gumbel noise, GI. Right, that's the entire point, where GI, like we mentioned, comes from some standard Gumbel distribution, so 0, 1. And what we want to show is the probability that y equals I is equal to e to the power OI divided by the sum over j e to the power oj. This looks exactly like softmax, right? This is our softmax. So we want to show by doing the argmax, if index I, or thing I, is the argmax, we want to show that the probability of selecting that I is indeed distributed with softmax. For any I, it doesn't really matter, but in this case, we're just going to be doing it for this one. And so this is what we want to prove. And let's just kind of go back again, just to compare it to the visual that we've looked at so far. Here we go. Don't need you. That is this right here, right? Me taking the argmax of O, which is 1, 3, 4, 2, and G, which is G1 through G4, taking the argmax of that will give me this probability distribution as I sample it over and over again. So essentially replicating that softmax distribution from before. So we want to show both of these things, two things are equivalent, and that's essentially what it looks like. So to do this, we need to do a little bit of, we need to know one property about Gumbel, and that's Gumbel shift property. Very simple, just like Gaussian distributions. If X is a Gumbel 0, 1 distribution, then X plus C is going to be a Gumbel C1 distribution. So we just move the mode over by whatever we added onto it. So this is the shift property of our Gumbel distributions. And we're going to take advantage of that. Because what are we doing? We're adding to Gumbel noise some OI, our logic. So if we're doing OI plus GI, right, where this is Gumbel, well, that's going to be distributed with a Gumbel, not 0, but 0 plus OI, or just OI, 1 noise, right? That's my distribution right there. And so what we can do is leverage this. We're going to use this to our advantage. And so what we're going to do first is say Zi, some variable Zi, is equal to OI plus GI, just like that. And that means this is going to be distributed as something like this. So we can say the probability of Zi being less than some arbitrary Z, doesn't really matter, is equal to the probability that OI plus GI is less than some Z, just like that. And we can turn these terms around a little bit, right? We can say this is equal to the probability that GI is less than Z minus OI, just like that. Now, what does this look like? The probability that X is less than X, well, this is a CDF, isn't it? Right? This is a CDF. Like if X, big X was a Gaussian distribution, then probably X is less than X is the CDF of the Gaussian distribution. And little p, X equal to X, is the PDF of the distribution. In this case, we're looking at a CDF here, right? This is the CDF that GI, which is some Gumbel random variable, is less than this value right here. So this is going to be the CDF, F, big capital F, Z minus OI. And where did this come from? This is just from earlier, where the CDF is big FX. That's where F is X less than X, right? Same thing. So this big FX represents the probability that X is less than X. This little fx represents the probability that X is equal to X, right? Standard PDF, CDF definitions. So this is exactly what that is, right? The probability of GI is less than something is just the CDF of that. So this is our shorthand. Now that we have that, we're going to be using some of these things to set it up. So first, what we're going to do is, this is the important part, step 1. We're going to express probability of Y equals K. So if we say that Y equals K, and remember, Y is equal to Arg-Max O plus G, right? OI plus GI. If Y is equal to K, that means OI plus, or I guess in our case, OK plus GK is greater than OI plus, or let's use a different letter just so it's clear, OJ plus GJ for all J not equal to K, right? If Y equals K, that means the Kth thing was the largest, which means OK plus GK was greater than OJ plus GJ for all K, for all J not equal to K, right? That's just how we're setting it up. Now, of course, we just created a little bit of a shorthand notation here, so we can also write this as ZK is greater than ZJ for all J not equal to K, just like that. And so if we say that ZK, our maximum, is equal to some Z, that also implies that ZJ is less than Z for all J not equal to K, which makes sense, right? If ZK is my maximum, if OK plus GK is my maximum, it's equal to some value Z. That means all the other ZJs must be less than Z, right? By definition, because this is my max. And so if that's the case, we can actually use this. This looks kind of like a PDF, right? Something is equal to something. So this is the PDF, and this is the PDF F Z minus OK, right? The probability of zk equals z is exactly this. It's what we had set up earlier. We have, we wrote it right up here. We wrote the probability of zi less than z. Well, we just have some zk less than z. And if zi less than z is fz minus oi, then zk equals z is going to be z minus OK, just like that, right? Z minus OK. It's just here we were looking at the CDF because it's less than. Here we're looking at the PDF because it's equal to. So this is our PDF, just like that, z minus OK, just like that. Similarly, this is a CDF, right? This is going to be fz minus oj, just like that. Again, for all j not equal to k. And this is a CDF because we're looking for zj less than z. So it's all of the density under z. So that's essentially how we want to think about it. We have our CDF, we have our PDF, and we set it up this way. Zk is equal to z, which is a PDF, and zj is less than z, which is a CDF. Now, one thing to keep in mind is when we do this, oi, or let's just write the simpler form, z1, z2, dot, 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 z, let's say there's n of them, whatever it may be, they're all IID because the Gaussian noise, or Gaussian, the Gumbel noise that we're adding to our data, to our logits, is randomly sampled. And these are IID, which means the sum is also IID. So these are all independent of each other. And so this is the last step that we have to think. What is the probability of zk equaling z and all the other zj's, where j is not equal to k, less than z? Well, it's the product of all of those events happening, right? All of these things have to happen at the same time. So we can write this as the probability that zk is equal to z times the probability of, and let's just write the shorthand notation, product j not equal to k, probability of zj less than z, just like that. So this is all the probabilities put together. This is the probability that zk is the maximum thing, which equals to some arbitrary z. And this is the probability that zj is less, all other j's, that's not k, everything else is less than z. And this is essentially how we're going to do it. And so the last thing we'll write is the probability of y equals some k. It's going to be equal to, and this was a PDF, so we're going to do f, and we wrote this as z minus OK, just like that, z minus OK, and then we have our product, j equals k, or does not equal k, there we go, j not equal k, and these are CDF, so it's going to be capital F, zj less than z, zj less than z, which we wrote as z minus oj. There we go. And that's our setup. Now, the question is, for what z? So we just introduced this random variable, right? Some variable here. It's not a random variable, just some variable, z. But for what z? Well, this has to be true for all z, right? For all z, if zk is equal to z for all z, then zj must be less than that same z for all z. So we need to add this up, right? Sum over all possible z's. If z was discrete, it would be a sum, but because we're dealing with continuous variables here right now, we'll do an integral over z. We want to add it up for all possibilities of z. So essentially what we're doing is for a specific z, we go ahead and compute our PDF, we compute all of the different CDFs, multiply them together, and then add it up for all the possible z's. In this case, z is on the, it's some real value, so we're going to go ahead and integrate. And this is the integral that we're going to be solving now. And that's where it becomes a little bit less fun because no one likes solving integrals. But to do this, we need to actually start filling some stuff in. We know the form for the CDF and the PDF, right? We know the formula for them, so let's go ahead and do that. This is going to be equal to the integral over z. And let's also say z technically goes from negative infinity to infinity, right? So let's just real line, so there you go. Anything that z could be. And we're going to have little f, this will be the PDF that we derived earlier. If we go up, this was the form for the PDF, e to the negative x times e to the negative e to the negative x. So we're going to do exactly the same thing. It's going to be e to the power negative z minus OK, just like that. And then e to the power negative e to the power negative, again, z minus OK. So that is our PDF, right? PDF. And then we're going to have the product of j not equal to k. And this is going to be on our CDF, which is going to look like, if we go back up, our CDF was again e to the power negative e to the power negative x. So it'll be that. It'll be e to the power negative z negative e to the power negative z minus o j, just like that. Now, something to keep in mind here is we have, and we of course have this dz at the end, we have the product of a bunch of exponentials. That's like e to the a times e to the b times e to the c dot dot dot. Well, that's e to the a plus b plus c dot dot dot. So we can move the product in and turn it into a sum. So let's do that step first. This is going to be equal to the integral from negative infinity to infinity e to the negative z minus OK e to the negative z minus OK. And then we're going to have e to the power negative, and we'll have a sum e to the power negative z minus oj, just like that. So this is again a sum. This is going to be sum of j not equal k, just like we had. But yeah, that's it. We've just moved the product into our exponential, so it becomes a sum. But notice a little bit of a grouping here. We have e to the power negative e to the negative z minus ok, and then we also have an e to the power something here. And these are also two exponentials multiplying together, so I can technically add the exponents together. So this is going to be equal to negative infinity to infinity e to the negative z minus ok. And it's going to be e to the power, and we have up here negative e to the power minus z minus OK. And then we'll have plus, or I guess minus, because this is a negative sign, sum j not equal to k e to the power minus z minus oj. Well, we have two negative signs here, so we can actually go ahead and erase both of them, take it out, and then just put a bracket around all of this plus. So we have a sum of e to the power negative z minus oj for all j not equal to k. But then we're adding on the thing that has the k in it, right? So this has everything but k, and here's my k. So I can just put that in the sum and just get rid of this j not equal to k. So in the end, this will all go away, and just become negative sum over j not equal to k, because now we've included the k term, e to the negative z minus oj dz, just like that. So that's the little bit of a simplification that we can do there. And just for simplicity, just for now, we're going to set, let's let sum j e to the minus z minus oj. Let's just let this equal to sz, just some function of z, just to keep things a little bit simple. And so what we can do then is substitute it in. Negative infinity to infinity, we'll have e to the power negative z minus ok. E to the power negative sz, right? So that's us plugging it in, and we'll have a dz right here. So now we need to evaluate this integral, which is where it becomes less fun. So this first part is not too bad. We need to do a variable substitution. So let's go ahead and do that. We're going to say u is equal to z minus ok. And this implies that z is equal to u plus ok, right? If we just move things around. And of course then dz is equal to du, right? The derivative of z is just derivative of u, so there you go, very simple. And we need to check our limits. As z goes to infinity, right? As z goes to infinity, then u will also go to infinity, so that's no problem. And as z goes to negative infinity, u will also go to negative infinity, right? So as z gets smaller and smaller, u will also get smaller and smaller. They're related to each other. So our integral limits stay the same. Du just becomes dz, and we're just doing a simple substitution. So this is going to be equal to negative infinity to infinity. We'll have e to the power negative, and my z minus OK just became u, so u. And then we'll have e to the power negative s. Instead of z, it's not a function of z anymore. We're going to plug in for z, u plus OK, u plus OK. And then dz becomes du, and our integral still goes from minus infinity to infinity because of our limit check here. So now that we've done this substitution, let's take a quick look at this. What is s of this stuff? Can we simplify it in any meaningful way? So like we wrote above, right, but I'll write it again here just so we have it in one place. Sz is just the sum over j of e to the power negative z minus oj, right? That was our sc. So that means s of u plus ok is going to equal to what? We just plug it in. We just do j, and we'll have e to the power negative. Instead of z, it'll be u plus ok minus oj, just like that. And that is going to equal to, we can do a little bit of simplification, j, we do the sum over j. Again, this will be e to the power negative u, and then we'll have times e to the power, and the negative distributes, so it'll be oj minus ok, oj minus ok, just like that. And again, for simplicity, right, for simplicity, let's let t equal to, right, equal to, and actually, just to make it more simple, there's no dependency. E to the minus u doesn't depend on j, so we can actually pull it out of the sum. So we can say e to the minus u sum j, e to the oj minus ok, right? So very simple. And let's let t equal to that sum of j, e to the power oj minus ok. Now, can we do something with this sum? Let's see if we can do something here. So we can first do, this is the sum of j, e to the power oj divided by e to the power ok. But ok has no dependency on j. It only the oj has dependency on j. So we can actually pull it out, and we'll end up with something like this. J e to the power oj divided by e to the power ok. And this looks like 1 divided by softmax, doesn't it? Right? This looks like the reciprocal of our standard softmax formula. So we're making some progress here. We're not there yet, but we're getting there. But we're going to let t equal to this thing. So t is kind of the inverse softmax for now. We're going to let it just for some shorthand notation. So what we have essentially written is s of u plus ok is going to be e to the negative u t, right? Just because we're using this t over here. So using our new variables, let's go ahead and plug it all in. This is, again, the integral will go from minus infinity to infinity. We had the e to the power negative u, and then we'll have an e to the power negative u t, just like that. And of course, we have our du right here. And now to actually integrate this, we need to do one more variable substitution, which is the less fun one, but that's okay. We'll get through it. We're first going to set v is equal to, I'll make sure my v's and u's look different enough, e to the power negative u. Let's say that. So that means u is equal to, we do the log and then take the negative, so it'll be negative log v. Du is equal to negative dv over v, right? That's what these are natural logs, right? So the derivative of it will be negative stays outside, 1 over v times the derivative of the inside is dv. So negative dv over v. That's my substitution. And now as u goes to infinity, v goes to what? So as u goes to infinity, e to the power negative infinity is 0. And then as u goes to negative infinity, v will go to e to the power negative infinity is infinity, right? So this is as u goes to negative infinity, v will go to infinity. So let's go ahead and reset our derivatives again. This is going to be equal to the integral, we'll set the limits in just a second. E to the power negative u is going to be our v, right? E to the power negative u. So this is going to be v. And then we will have our e to the power negative. In this case, we have negative t v. Okay, yes. Actually, I made one small mistake. Let's fix that. This is e to the power minus u t, right? Which makes sense. So this should be e to the power minus u t. Yes, I made a small mistake right here. Let's rewrite this. This is going to be the integral from negative infinity to infinity, like we had earlier, and it's going to be e to the power negative u first, so it's going to be, and then we will have e to the power negative all this stuff that we did. So it's going to be e to the power negative e to the minus u t. There we go. That's more correct. Sorry about that. So that clears up that problem. And so now we have, everything else stays the same. We're still good. So now we have v, e to the negative u is just v. And then we have e to the power. We have another e to the negative u. So that's going to be negative v. And then the t is still just there. So we have t. And then what was du again? Du was negative dv over v. So that's going to be times negative dv over v. And so we can set this up, right? We'll do a little bit of simplification. We have this negative sign here. So we're going to pull the negative out. We'll fill in the limits of the integral in just a second. We'll have v e to the power negative tv dv. And now we have also times a 1 over v, right? So we can actually delete this 1 over v and this v right here, because this v and this v would have canceled. And so we're left with just this, e to the power negative tv dv. And the integral went from, as u went to infinity, v went to 0. And as u went to negative infinity, v went to infinity. Now this is kind of weird, right? We kind of have it backwards, infinity to 0. So if we flip it around, we also have to flip the sign. So this is going to be equal to integral from 0 to infinity, e to the power negative tv dv. And this is finally an integral we can easily solve. This is just going to be equal to negative 1 over t, right? That's the integral. And it's going to be e to the negative tv from 0 to infinity, right? So the integral of e to the power minus tv is negative 1 over t, e to the negative tv. 1 over t is just a constant, so we can pull it out. And the negative is a constant, so we can pull it out. And we're left with this. And this is going to be negative 1 over t. And then we will have, when it's infinity, it'll be 0. And when it's 0, it's 1, which means it's going to be equal to 1 over t. And what was t? T was equal to 1 over softmax, right? Just like we saw before. So 1 over t is equal to softmax. And we have essentially proved it, right? We have proved that the probability of y equals k will just equal to e to the power, ok, divided by sum over all j's e to the power oj. And this is via the Gumbel trick. So the Gumbel-Max trick gives us exactly the same result as softmax. It's just a different way of doing it, which is awesome, right? So we've now proven it. You now know why it works. And so we're going to go ahead and start implementing bits and pieces of it. I think there is one other thing we need to, there's actually one other thing we need to talk about. How do we sample from a Gumbel distribution? So let's talk about that now. So we've proven that they're equivalent, right? We've proven they're equivalent, but I need to do OI plus GI, right? So where do I get GI? Well, how do you normally do it? You'll go to like torch.distributions.normal, and you'll use their normal distribution or their Gumbel. So we could just use their distribution. Obviously, we can just use an existing one, but it's probably interesting to know how do we sample this Gumbel noise. So let's go ahead and check. What we do is use the inverse transform sampling. So the reason we can use ITS in this case, or the CDF method, which is another way it's typically known, is because the Gumbel distribution has an invertible CDF. The normal distribution doesn't. So the normal distribution doesn't have an invertible, it's not an invertible distribution, which is why we have to use tricks like the Box-Mueller trick or whatever to actually sample from a Gaussian distribution. But the Gumbel distribution is easy to work with. And so let's go ahead and see how we sample from it. So if you've never seen the CDF trick before, it's actually kind of cool. The CDF of a distribution, fx, has to be between 0 and 1, right? The CDF is bounded between 0 and 1. So if I take the inverse, assuming the CDF is invertible, of course, but if I take the inverse of f of x, well, this is going to be f inverse 0, 1, right? It's going to be within 0, 1. And this means x, which is the thing I want to sample, right? X is the thing I want to sample, is inside this, let's write it this way, 0, 1 distribution. And so if I know this to be true, what if I pick random values between 0 and 1, invert it, and that gives me my sample x? And that's exactly what we do. What distributions do we know uniformly samples between 0 and 1? Well, uniform, right? We'll just take a uniform 0, 1 distribution. We'll randomly pick a number between 0 and 1, pass it through the inverse transform, and ta-da, we have now sampled a value from that. So in the same way, we want to sample from our Gumbel distribution. So we know our CDF, fx, which is element, it's inside 0, 1. It's equal to, right? It's e to the power negative e to the power negative x. That's our setup. And so if we want to take the inverse of this, well, we just need to take a bunch of logs, right? We can take the x will be inside negative log of negative log of 0, 1, just like that. But that's it. We're just taking log, right? We want the x on its own. So if we take the log of this, then the log of e to the power negative e to the power negative x is just going to be the numerator, right? Negative e to the negative x. And then we have a negative term. So we have a negative log now. And so then we're just left with e to the negative x. Again, take the log of it. Then we have and if we take the log of it again, we'll end up with negative x. Again, we have a negative term, so multiply by a negative 1. So there's the first negative, there's the second negative, and then we're just left with x, right? Very simple. And we know this is uniform, right? Anything between 0 and 1. So that's how we will sample from a Gumbel distribution. It'll be negative log of negative log of u. That's how we will grab samples from a Gumbel distribution. You can also just use an existing, package that does it, but this is exactly how they do it internally. Nothing fancy. And this only works out so easily because Gumbel distribution is one of the many distributions that are nicely invertible. So that's why we can use this. So to go ahead and kind of prove to you everything we've seen here so far is this. So I won't write this code. We'll just kind of look at it. What I want to show is our softmax gives the exact same values as our logits. So all I did is here are my logits, 1 through 5. So these will be the raw outputs of the neural network. I'm going to sample 10,000 samples. And what we're going to do is Gumbel-Max. We're going to grab 10,000 samples worth of uniform noise. We're going to go ahead and do our transformation. So we're going to do uniform. Again, we do uniform, negative log, and we just add an EPS to make sure there isn't like if 0 shows up by accident, then log wouldn't work out anymore. And then we got our Gumbel noise. And so then we're going to add to our logits our Gumbel noise. We're going to take the argmax to see which thing was predicted, right? So the thing with the highest is the thing we selected, and we're going to return those. Similarly for softmax, we're just going to go ahead and take the softmax and then sample from that softmax distribution over and over again. And of course, that should give you the same distribution that the softmax returns. And we can go ahead and plot those out, and you can see they're very close, right? The softmax and Gumbel-Max give essentially the same probability distribution, even though we're doing it in 2 completely different ways. It's just that doing this is typically a lot cheaper than doing a softmax than a multinomial, which is why this is preferable and used a lot in LLM decoding and stuff like that. It's used a lot in reinforcement learning, and we're going to be using it today for all this. Now, this all seems well and good, but we still have a little bit of a problem. We've only talked about Gumbel-Max. Now we need to move to Gumbel Softmax. And so Gumbel Softmax does exactly what you think, nothing fancy. The problem with Gumbel-Max is I have shown that y equals argmax I oi plus gi. This is essentially modeling a soft max, right? This is a softmax distribution. The problem is this argmax here is not differentiable, right? We can't take the derivative of an argmax. So we're still back to the same problem. The Gumbel-Max does not solve the VQVAE problem of sampling a categorical distribution. It just makes sampling from a categorical distribution faster. But this argmax is not a differentiable method. So all we do, and essentially what the Gumbel Softmax proposed, is why not just convert it to a simple softmax. So this is going to be equal to e to the power oi plus gi divided by some tau, and we'll see what that tau is in just a second, divided by sum over j e to the power oj plus gj over tau, just like that. And this is differentiable. Everything I've done here is differentiable, but we've lost some stuff, right? We've lost like the max nature of it. And this is why we use tau, which is known as the temperature parameter. So tau is temperature, which allows us to sharpen or to essentially smooth out a distribution, right? So if tau is large, that means we have a big denominator and it'll divide everything, and our distribution, our overall distribution, is going to be cooled. It's going to be cooled and become kind of like uniform. So when tau is large, this is going to be close to uniform. The distribution of all the different possible y's will be close to uniform. And when tau is small, it'll be close to a one-hot-encoded vector. Like 100% of the probability will be on one thing, and almost 0 will be on everything else. And so this is the key idea. When tau is large, the distribution is close to uniform. When tau is small, it'll be close to one-hot encoding. And the important part is that we typically don't set the tau ahead of time. It's decayed over time. And so we'll kind of talk about that in just a second. But this is essentially our change. This is our Gumbel Softmax, which did absolutely nothing but change our argmax to a softmax, and we now have this temperature parameter tau. So let's go ahead and just see visually what this temperature parameter is doing, just so you can understand the importance of it. And so I'm going to go ahead and implement Gumbel Softmax, right? And once we've implemented Gumbel Softmax, we can go ahead and do the temperature parameter. So what we're going to do is def Gumbel Softmax. It's going to be, we're going to pass in some logits, some tau, which we'll set to 1 by default. I'm going to have this hard parameter here right now, which we won't talk about just yet. We'll see why we need it in a bit. We'll have some EPS so we don't have any log errors, and dim is -1, right? And so how do we sample? We take our logits and we want to add some Gumbel noise to it. So we need some Gumbel noise. So rand uniform is going to be equal to torch.rand like, so uniform, logits, and device is equal to logits.device. Just make sure if we're doing it on the GPU, then it's all right there. And Gumbels is equal to negative torch.log, negative torch.log. We'll have our rand uniform plus EPS, just like we had, and another plus EPS right here. So that is exactly what we had described earlier, right? Negative torch.log, our random plus EPS, plus EPS, just to make sure there's no zeros. Now that we have that, we'll do y is equal to f.softmax, because we're going to be taking the softmax of this, of our logits plus Gumbels, right? Logits plus Gumbels, and we're going to divide it by tau. and we'll do it along the dim equals dim. Whatever we provide, typically we just do it along the last dimension, so we don't have to think about it. And we will now return y, just like that. So that's our standard, it's very simple Gumbel Softmax. We had our logits, we added Gumbel noise to it, we do Softmax, and that gives us our final output. And so now, what do we do with this? Well, let's go ahead and plot the effects of tau. And what I've done here is I'm going to grab, this is just a visualization code, so I'm not going to write it out for you to watch. We're going to sample 1,000 values. We're going to try a bunch of different taus on these logits. We have our true distribution. We can take the softmax and see that. And what we're going to do is just see what the tau parameter does. Looks like we have a bug, or I guess I forgot to do some imports. So let's, I think I forgot to run maybe the first cell. There we go. Okay. Okay, I think that worked. Okay, there we go. All right, so we can see the true distribution is basically 1% to the first thing, 3% to the second thing, 8%, 23%, 63%. And we can see when we have a small tau, we're getting pretty close to that, right? That's kind of the distribution we're getting. But as we increase tau, notice how our distribution becomes closer and closer to uniform, because we're essentially cooling the distribution, right? This is the same reason we do like not weight penalties, but like when we do smoothing and things like that, it's because we're trying to make our distribution a little bit more uniform rather than sharp. And if we pick an even smaller tau, like 0.001, you can see it gets further accentuated, right? Further accentuated. And so that's the main idea. Tau is a cooling parameter. As we increase tau, our distribution becomes more and more like this. Now, why is this a little bit of a problem? Or not really a problem, but why do we even want it to work like this? It's because we typically train our model in this way. Imagine that, now let's go back to the VQVAE. We have 5 different codes to pick from, right? 5 different codes to pick from. That's our code book. So at the beginning of training, it's not like the neural network knows which code is good and which code is bad, right? It just began, it doesn't know anything. So by having a closer to uniform distribution, what we can do is make it a little more random, right? The model doesn't have to commit to a specific code. It's totally fine if it doesn't commit to a specific code, right? Because it doesn't know anything yet. But as we train, we typically decay this tau parameter, so the model is forced to actually commit to a specific code. That's the main idea. Now, an issue we have is this. So let's go back here. The Gumbel Softmax will return a probability distribution, right? What's the probability of picking the first thing, second thing, ... That technically works for a lot of applications, but not for the VQVAE that we're looking for, to access codebooks. Because to access a codebook, we kind of want to select a specific code. Now, we could leave it like a probability distribution. Say I want, if it was like 10%, 20%, 40%, whatever, then I could say I want 10% of the first thing and 20% of the second thing, ... But then it becomes a linear combination of the codes, and it's not exactly a VQVAE anymore. You're not committing to a specific code. So what we want is a one-hot-encoded vector. We want zeros on things that are, the things we don't want, and 1 on the thing with the highest probability. And so to do that, that's why we have this hard equals true or false. So if hard is false, it will return a probability distribution. If hard is true, it'll return a one-hot distribution. So let's see what that looks like. Let's create some logits. Torch.randn, and let's say we have one sample with 5 outputs, and we're going to do Gumbel Softmax on these logits. So we've returned a distribution, right? That's my distribution. And what I want is, instead of returning it like this, I want a 1 on the most likely thing and 0 everywhere else. So let's go ahead and do that. If hard, right? So if hard is set to true, then we're going to do y hard is equal to torch.0. So let's go ahead and do that. Y device equals y.device, just like that. And our max index is going to be equal to y.argmax dim equals dim, keep dim equals true. And so if we print y, or max index, you'll see this. So we have logits, and we're going to do hard equals true. looks like should be torch.zeros like. There we go. So we have, and we can see here, let's see here, our 0, 1, 2. So yeah, this is the highest index, so index 2 is the highest. And what we want to do is in our y-hard, place that max index as a 1, and everything else should stay as 0. So y-hard dot scatter, right? So dot scatter, we provided the dimension that we want to do it along. So in this case, it's along the last, these refer to the last dimension, right? So that's where it is. And then max index is the thing we want to fill with, and then 1.0, right? So we want to fill with the 1.0 at the max index, and these index numbers refer to the last dimension of our y-hard. So if we print y-hard, you'll see we have a 1 on the thing that's max and 0 on everything else. So we can see this thing was the max, so there we go. Now, as you can imagine, this thing we just did here of indexing is not a differentiable function, right? This again, this argmax is not differentiable, so we need to copy our gradients over. So y equals y plus y hard minus y dot detach. So this should feel familiar to you because we saw this in our VQVAE implementation, detach, sorry. But the idea is y, which is our original data, is going to be equal to y plus, and then we do dot detach on all this because this operation between y and y hard is not differentiable. But this is like saying y is equal to y hard, but we're copying the gradients over from y onto y hard. So that's the main idea. So again, if you're confused on any of this, just go ahead and look at that VQVAE implementation. But that's all this is. This is just me copying gradients over. We could also write a custom backward function, but there's no need to do that for simple things like this. So this is my straight through estimator for hard. This isn't a big deal because, again, this is just a simple gradient copy on a relatively simple indexing problem. I just want my gradients from this to flow through all of this. So in the forward pass, the model will see 0, 0, 1, 0, 0. But in the backward pass, it's going to see these actual values because these values were what created those gradients. And so this isn't nearly as obtrusive or annoying as the same operation we did in the VQVAE, because in VQVAE we had to do that Argmin operation, and it's much more complicated and expensive. So this is much simpler. So we have everything we need, and now we get a one-hot encoded vector of 1 for the thing we want and 0 everywhere else. And that's it. That is our Gumbel Softmax. So now that we have Gumbel Softmax, I'm going to be training a model. At this point, the code will be very, very similar to before. So I just want to write the Gumbel Softmax Quantizer. We will copy in the convolutional encoder decoder stuff that we had from the VQVAE. So if you again remember back to our VQVAE, we wrote a convolution. That's the linear one. Let's just skip to the convolution somewhere here. Here we go. This convolutional vector quantized VAE. We're just going to copy paste exactly this. We're just going to replace our VQ from the vector quantizer to our Gumbel Softmax Quantizer. That's all. So let's go ahead and write the class Gumbel Softmax Quantizer, and then .module, def init, self, we'll have a codebook size, and we'll have an embedding dimension, right? And we'll have use super.init, just like always. And we'll do self.codebook size is codebook size, self.embedding dim is embedding dim. And lastly, we have our self.tau, which we'll just set as 2.0 by default. So we're going to decay tau from like 2 to 1 or 2 to 0.5 or something like that. And you can kind of play with that yourself, but that's what we have, tau. So self.proj is going to be nn.linear. It's going to take in an embedding, right? Embedding dim. It's going to take in an embedding from our output of the encoder, and it's going to output it to codebook size, right? Just like we had in the visual up here. It's going to take an embedding. So the input is the embedding dim, and the output is the number of codes that we have access to. We're going to use Gumbel Softmax to figure out which code we want to pick, and then we will actually pick that code. And that's the main idea. So we have that right there. Similarly, we'll have self.embedding. This will be the actual codebook, nn.embedding. And we'll have codebook size and embedding dim, just like that. So def forward self x. So we'll have batch size is going to be x.shape 0, right, like always. And our logits is going to be self.proj_x. So let's verify how we do this. We're going to do rand is torch.randn. And let's say our data comes in the batch size of like 4 by 12, right? Let's just say that. So our embedding dim is 4 and our batch dimension is, or sorry, embedding dim is 12 and our batch dimension is 4. So that means we're going to have our layer is going to be the Gumbel Softmax Quantizer. And let's say the codebook size is 32 and the embedding dim is 12 because that's what it is. And so we're going to pass into here our rand. And if we print our logits.shape, we can see for every embedding vector, we have 32 possibilities because we have 32 codes in our codebook. So that's what we're going to use. Now here's a discrepancy. If we're training, if self.training, right, if we're in training mode, then we'll do one-hot-encoded codes is equal to the Gumbel Softmax, just like we did. It'll be our logits. Tau is equal to self.tau. And hard is equal to true. And if we print OHE codes, we'll get exactly that. We have 32 possibilities for each code, and we have a 1 for the code we selected, and we have a 0 for all the other codes. So each embedding has 32 possibilities, 1 on the one we want, 0 on everything else. And it's as simple as that, right? We have our one-hot-encoded vector. But if we're not training else, then we don't really care about gradients, right? The entire point of Gumbel Softmax was like, we wanted to train our model, have gradients flow through that sampling process. But when we're inferencing, we don't really care about that, right? Because it gives us the same thing. So what we can do is OHE codes is, and this is going to be just like before, torch.zeros, zeros like logits, and we'll make sure it's on the right device. Device is equal to logits.device. And then we'll do our max index as logits.argmax dim equals -1. Keep dim equals true because we need that dimension to stay. And OHE codes is going to be dot, just like before, scatter. And we're going to copy in along the last dimension the max index for each sample, and we're going to fill them with 1.0. So basically, this is doing exactly this, just in a differentiable way. And when we're inferencing, we don't really care about taking the derivative. We just want the max logic, the code vector that's most likely to be selected. So that's why we're going to do the argmax here during inference time. Now that we have that, we have these OHE codes. And so the last part is our quantized. If we are, let's just check OHE codes.shape and self.embeddings.weight.shape. Should make it clear. Our codebook is basically zeros and ones, and we have 4 by 32 of them. And we have 32 codes and 12 of them. And each one has an embedding of 12. So that would do something like this. We have 4 by 32. And they're 0 everywhere except for the thing we care about. Let's say something like that. And we have a embedding matrix, right? That's 32 by 12. So if I do a matrix multiplication, that will give me a 4 by 12 matrix where I'm going to multiply. In the first one, I want this index, right? So we'll have 0 times the first embedding, 0 times the second embedding, 1 times the third embedding, and then 0 times everything else after that. So that's essentially 0 times everything except for the one thing that I care about, right? This index right here. Similarly, for the next one, it'll have for this one, and this one will have it for this one, ... So just doing a simple matrix multiplication essentially does the index operation for us. So we can do a very simple. This is going to be quantized is equal to torch.mapmul. I mean, we can index it in all sorts of ways, but this is the easiest way. So OHE codes self.embeddings.weight, and if we print quantized, we see we have selected our embedding vectors. Now our model obviously has not been trained, so these quantized vectors don't mean anything, but it's all we need. So we can now return quantized and the OHE codes, just like that. And this is our Gumbel Softmax Quantizer. Now everything going forward is identical to what we had done before. So we're just going to keep all of it. So if you're confused on any of this code about the convolutional VQVAE stuff, just go ahead and watch that VQVAE video. Again, assuming you came from there. All I changed is my VQ is now my Gumbel Softmax Quantizer, right? Just like that. And so if we do rand is torch.randn, let's say our data is 4 by 1 channel by 28 by 28. Or actually, let's do 32 by 32 because that's how I prepped it. Then our model is going to be this convolutional Gumbel VAE, and I select a in channels, latent dimensions, codebook size, tau, all that sort of stuff. And actually, we don't really use tau for anything, so you can ignore that. We can then set it right here. And so we have our model. If we look at it, again, identical setup to before, just a bunch of convolutions, transpose convolutions with ReLUs in between, and we have this Gumbel Softmax Quantizer. So we can take this model, we can pass in rand, and we get this output, right? We get all of these different outputs that we care about, and that's fine. We don't really need all these outputs. All we really need is the quantized latent, so you can see the what those embeddings look like, and we need this OHE codes if you want to know what the specific quantized vectors were, and decoder if you want to visualize the final output. So that is our setup. Our training script will be identical to before, so we can go ahead and do that again, but we just have one extra thing. We want to anneal our tau values. So we'll do def train, I'll write some of it out. Model, train set, test set, batch size, training, iterations, evaluation, iterations, tau start, we'll start at like 1, and tau end, we'll end at like 0.5 or something like that. And percent decay steps is, let's say, 0.5. So what this means is I'm going to start my tau at 1. I'm going to decay it to 0.5 in half the steps. If I'm training for 200,000 steps, the first 100,000 steps, it's going to decay from 1 to 0.5. And then for the second set of 100,000 steps, it's going to just stay at 0.5. And that's it. So then we can do standard stuff. Our device is going to be CUDA model equal model dot to device. Then we have our train loader, and I can go ahead and actually copy some of this boilerplate code in. So we have our train loader, we have our data loaders, optimizer, all that sort of stuff. Here's the important part. We have our decay steps. It's going to be the percent. So it's going to be percent decay steps times our training iteration. So how many steps over which do I want to decay? And so then tau decay is going to be np.linspace, because I'm going to just do a simple linear decay. You could also do exponential or pick some other scheduler if you want, but we're going to do tau start, do tau end in those decay steps. And then what we're going to do is our tau constant. It's going to be torch.full training iterations minus decay. So for the other 50% of the steps, right? So that's how many steps you have left over, total iterations minus the decay steps. We're going to fill it with just tau end. So it'll just stay at 0.5 the entire time. So our tau schedule will finally be np.concatenate. It'll be the tau decay, right? Decay from 1 to 0.5 in half the steps. And then tau constant, just stay at 0.5 for the remaining steps. After that, everything else about our training is identical. So we can do this here real quick. So we're going to first start our training while less, set our model in training mode. For every image, if step is greater than or equal to training iterations, just go ahead and break, because that means we're done. And we can do a quick model.vq.tau is equal to tau schedule step. And this part is crucial, right? This is me updating my tau parameter in the vector quantizer. Remember, again, if we go up here, we have that as a parameter right here. So we're just going to go ahead and update that every single step. So it'll start at 1 and then decay down to whatever it needs to be. And so after that, everything else about training is identical. Nothing fancy, right? Just standard training loop. Grab images, grab the passive in, grab the outputs. We're only doing mean squared error as our reconstruction loss here. Nothing fancy, so there you go. We then have our loss, update our model, 0 red, print it out, evaluate, that sort of stuff. And no one wants to watch a training loop, but let's just verify that this is indeed working. So we're just going to run it with the batch size of 64 on this. Let's see what our train is not defined. Okay, not run you. All right, so let's see what's wrong here. Full argument size must be a tuple or int. Okay, let's check that. np.full, or sorry, this should be np.full. There we go. Tau decay, and spelled it wrong. So that's going to be tau decay. And there we go. Now we can see it's starting to train. We can see the tau is slowly but surely decreasing, right? So nothing too crazy. Obviously, no one wants to watch a training loop. That's no fun for anyone. So we can just look at some of the final results, and we can see it comes up with the reasonable, quantizations. Nothing fancy, just good enough. So this was, again, not a very quick, but a somewhat helpful coverage of the Gumbel Softmax. The only reason I really covered this is because the wave-to-vec architecture that I actually want to cover leverages this. So the wave-to-vec architecture uses Gumbel Softmax in its quantization procedure. So quantization of speech is extremely important. It kind of powers a lot of major architectures out there. And there's all sorts of methods you can use to quantize. In this case, they decided to use the Gumbel Softmax Quantization just because it's stable, lets you pass derivatives, and it's just easier to work with when it comes to this sort of stuff. So you can see we do some convolutions and we have all these Qs. Well, these Qs are quantized speech representations that were produced via Gumbel Softmax. And it looks exactly like what we did. It's just applied on speech rather than on images, but it doesn't really make a difference. So yeah, that was the main motivation for this. There is a couple of small things though when it comes to Gumbel Softmax. There is the idea that we have a code book, and just like in VQVAE, neural networks are not inherently going to explore the full breadth of the code book, right? That doesn't always happen. So you need to give it a little bit of motivation to actually explore the code book rather than just sticking to a couple codes and falling into something known as index collapse. And so in that situation, we need to add some losses. In the case of wave-to-vec, they add the diversity loss, right? The diversity loss essentially is designed to increase the use of the quantized codebook representations, right? So there's diversity loss, there's perplexity loss, there's a bunch of ways to kind of represent that. So we'll be essentially implementing all of this in the future, so you'll kind of see exactly how it works. But that's the main idea, right? There's this loss function that exists just to help motivate the model to explore the codebook rather than just selecting a couple codes and not using it. Either way, I am going to call it here. That was essentially, again, a coverage of the Gumbel Softmax, very important method of doing differentiable categorical sampling for training and things like that. So I will see y'all in the next one.